Let's jump right in. Welcome to today's explainer. Think about the fiery chaos of combustion for a second. I mean, it's literally the beating heart of our modern world, right? It drives everything from the engine in your car to those massive power plants keeping our cities lit up. But if we strip away the roaring flames and all that intense heat, we're actually left with this fascinating, highly precise mathematical reality. The real question is, how do we take something as wild and, well, destructive as fire and accurately evaluate the chemical reactions and the energy balance? How do we precisely measure and maximize that power? And that right there is the ultimate engineering challenge. You see, it's not just about making things burn. Any kid with a magnifying glass can do that. It's about calculating the absolute perfect fuel-to-air mix, tracking literally every single joule of energy as these chemical bonds violently snap and reform, and ultimately capturing the absolute maximum amount of useful work from that reaction. To truly wrap our heads around thermal combustion, we gotta look way past the flames and decode the thermodynamics actually governing the whole shebang. So here's our roadmap for today's explainer. We're gonna hit the chemistry of combustion, the air-fuel ratio, enthalpy and energy balances, adiabatic flame temperature, and finally, wrap it all up with entropy and chemical exergy. All right, sections 1 and 2, chemistry and the air-fuel ratio. Let's dive right in by setting some essential chemical ground rules for reacting systems. Because before we can measure the energy of a fire, we absolutely have to know exactly what's going into it and what's coming out. The foundational concept we need to start with is complete combustion. Now, this is the ideal scenario. It's basically the engineer's ultimate dream. It happens when every single drop of fuel is fully 100% oxidized. So if there's carbon in the fuel, it all becomes carbon dioxide. Every last bit of hydrogen turns into water, and any sulfur becomes sulfur dioxide. You get zero leftover unburned fuel. But to get this absolutely perfect reaction, we need oxygen. And here's the catch. In almost all practical applications, we aren't using pure oxygen, right? We use ambient air. Dry air is roughly 21% oxygen and 79% nitrogen. What that means is, for every single mole of oxygen we drag into our combustion chamber, we are forced to bring along 3.76 moles of completely inert nitrogen. And that nitrogen, it doesn't help the fire burn at all. It's basically just tagging along for the ride, soaking up our precious heat, and frankly, complicating all our math. Think of combustion kind of like baking. You need an exact, super strict recipe. We call this recipe the theoretical amount of air. It is the absolute bare minimum amount of air required to pull off complete combustion, with not a single molecule of oxygen left over at the end. When looking at the balanced equation for methane here, you can clearly see the oxygen requirement. But check out the nitrogen multiplier. To get the 2 moles of oxygen we desperately need, we are forced to ingest 7.5 moles of nitrogen. That's a lot of dead weight. But you know, in the messy real world, trying to run a fire on the exact theoretical air almost always leads to incomplete combustion. The fuel and air just don't mix perfectly. So what do engineers do? They use excess air. For instance, methane burning with 150% theoretical air, which is basically 50% excess air. Notice what happens to the products on the back end. All that extra oxygen plus a massive, and I mean massive amount of accompanying nitrogen, 11.28 moles of it, just carries straight through to the exhaust. And as we'll see in just a bit, carrying all that extra baggage has massive implications for the actual temperature of our fire. Moving on to section 3, enthalpy and energy balances. Now that we have our chemistry balanced, we can finally transition to tracking the thermodynamic energy as these chemicals react and fundamentally change their form. Okay, so here is our really fascinating thermodynamic plot twist. Up until now, when dealing with standard non-reacting systems, you could just pop open a textbook and look up the energy of steam or refrigerant in standard tables. Those tables use completely arbitrary baselines, like, deciding water at its freezing point just has 0 energy. And that works perfectly fine, because in a closed loop, we only care about the change in energy, so the arbitrary baseline just naturally cancels itself out. But in reacting systems, everything changes. Chemical bonds are violently breaking, brand new molecules are forming, so those standard tables completely fail us. We actually need a brand new universal baseline to evaluate the energy balance. To solve this huge headache, engineers came up with the enthalpy of formation. I actually like to think of this using a sea level analogy. Just like cartographers assigned sea level as a universal 0 point so they could measure both huge mountains and deep ocean trenches, thermodynamicists assigned an enthalpy value of exactly 0 to stable elements. We're talking things like hydrogen gas, oxygen gas, and solid carbon, all at a standard reference state of 25 degrees Celsius and 1 atmosphere. So when hydrogen and oxygen react to form water, the energy released during that formation from its base elements gives us the water's enthalpy of formation. Boom. Now, every single molecule has a universal energy coordinate. Let's actually see this universal baseline in action. Imagine a steady-state reactor, essentially just a combustor, burning pulverized carbon. Carbon and oxygen enter, they react, and carbon dioxide exits. By knowing the exact universal enthalpy of the carbon and oxygen coming in and the newly formed carbon dioxide going out, we can figure out exactly how much heat this reaction is pumping out. And to pull that off, we use the energy rate balance equation. Let me just play tour guide for a second through this seemingly messy formula. On the left, we've got 0, simply because it's a steady-state system. On the right, we have our heat transfer and work, followed by the specific enthalpies of the carbon, oxygen, and carbon dioxide flowing in and out. Now, in a standard combustor, we aren't producing any mechanical work, right? So we can literally just cross that work term right out. Same goes for kinetic and potential energy changes. They are completely negligible here, so toss them out too. So the really crucial point here is that when we rearrange this newly simplified equation, calculating the exact heat transfer simply comes down to comparing the total enthalpy of the exiting combustion products against the total enthalpy of the entering fuel and air. It's honestly just an elegant energy accounting system. Every bit of heat radiating from that fire is mathematically equal to the difference in those specific enthalpies. All right, section 4, adiabatic flame temperature. This brings us to the real climax of our energy evaluation, discovering the absolute physical limit of thermal output for any given fuel. So if you want to know the absolute hottest a fire can possibly get, you calculate its adiabatic flame temperature. This is the theoretical maximum temperature achieved by combustion products in the limit of perfect adiabatic operation. And adiabatic, if you recall, means absolutely zero heat is lost to the surroundings. Literally all the energy released by breaking those chemical bonds goes directly into heating up the exhaust gases. This massive maximum peak strictly occurs during complete combustion, using the exact theoretical amount of air. No more, no less. And this brilliantly illustrates the hidden cost of straying from that perfect theoretical air mixture. Just look at the curve for methane. The temperature peaks right at exactly 100% theoretical air. But remember earlier when we were talking about how real-world engines use excess air just to ensure the fuel actually burns? Well, as you start dumping in 200%, 300%, or 400% theoretical air, that maximum temperature drastically drops off. Why? Because all that excess oxygen and all that heavy inert nitrogen act like a diluting batter. The chemical energy released by the fuel is totally fixed, but now it has to heat up a much, much larger volume of gas. And more gas to heat simply means a much lower overall temperature. Which brings us to our final section, Section 5, Entropy and Chemical Exergy. Let's take everything we've learned and see how it builds into the ultimate engineering reality check. We're going to look at exactly why maximum heat energy alone doesn't translate directly to maximum useful work. To really get this, we have to contrast the first law of thermodynamics with the second law. Under the first law, energy is always conserved, right? We're basically just tracking total heat transfer. But the second law introduces this really sobering concept, Exergy. Exergy tracks the actual potential to do useful work, like, actually turning a turbine or moving a piston. And unlike energy, Exergy is definitely not conserved. Thanks to our old friend entropy, Exergy is permanently destroyed by irreversibilities in a system. When we start looking at the exergetic efficiency of an engine, it completely changes how we view combustion. Think about it. We put highly organized chemical exergy, the fuel, into the combustor. But the sheer violence of combustion, the massive temperature gradients, and the totally uncontrolled mixing of molecules create massive amounts of entropy. Actually, the biggest irreversible loss of potential work doesn't even happen from friction in the gears. It happens right inside the fiery chaos of the combustion chamber itself. The exiting combustion products might still be incredibly hot, but their actual potential to do highly organized, useful work has been permanently degraded. And that perfectly bridges the gap between raw, wild heat and calculated, useful work. We can perfectly balance the chemistry, and sure, we can track every single joule of enthalpy, but the second law of thermodynamics always exacts its toll. The sheer act of burning destroys a massive portion of the fuel's true potential. So, I'll leave you with this. Next time you see a hot exhaust pipe on a car or a smokestack on a power plant, ask yourself, how much pristine chemical potential was just permanently destroyed and completely wasted to the environment? It's a pretty profound reminder of the inherent inefficiencies of our universe and the incredible, never-ending challenge of pushing the absolute limits of modern engineering. Thanks so much for joining me on today's Explainer. And, as always, keep questioning the science around you.